Okay, it looks like we've got everybody in. I'm hopeful that somebody can shout out and so they can see the screen.
And you
Yep,
can
see the screen.
Yeah, good. Okay, I'll
Yep.
get us started then. So, I'm just going to do an introduction, just for 5 minutes or so, and then we'll get on with the speakers that we've invited to talk about the technology. That's me. For those who don't know me, Tim Sargent. I'm the vice chair of UK STT, so I'm delighted to act as a sort of host on this particular event for the new to trenchless group. And we'll very briefly mention the sort of philosophy we have around that and why we have it. We started coining this as non-cured in place, and then we sort of thought, well, maybe that's a bit confusing because if you're new to, you might not even know what non-cured in place was. So we've rephrased it, the latter end to pressure pipe technology. It will give some examples of that. It's by no means an exhaustive thing that we're going to do today, but we are going to give you a taster of a couple of technologies that have been around for quite some time, and therefore, we hope, not too scary for those of you who are new to this tech. Quite interesting, the group that we have on today, 40 odd plus come in. We've had a look at who's on it, and it's great. It's a really good mixture of network owners, there's some designers amongst you, contractors, one or two suppliers, and it covers the whole range of individuals. And that's really important to us, because you all have a role to play in the decision making as to whether trenchless is the option, and or what that process or technique might be ultimately to do.
Take care. Bye.
Some housekeeping, just perfect timing there for whoever was unmuted. If you could put your microphones on mute, just double check if you would. We will have a panel Q&A at the end, so we will, we can open it up then. But in the meantime, and we suggest this works quite well, please do use the chat box, because as you think of things, even if the speaker's in full flow, feel free to drop it in, because we know, if you have a thought about something or a query about something, they might answer it, obviously, as they progress, but feel free to sort of drop something in there. And then we will endeavour as a team to pick that up at the end.
Tim, you've just muted yourself somehow, or someone's muted you, so we can't hear you anymore.
You're on mute, Tim.
We still can't hear you, Tim, sorry.
Right, back on? Yeah.
Yeah, we've got you now.
Yep.
You've also stopped sharing the screen.
Yeah, I'm just going back in. Just bear with me. Yeah, just bear with me. I'm just reloading it. Joys of technology. And come back in. Just bear with us. Okay, is that back on?
Yep.
Yeah, apologies about that. Okay, so let's see if it's going to behave now. So we've got the mutes, we've got the chat, slides will be circulated afterwards. Also, we've got your contact details. If you've joined us late, feel free to pass those through so we get you on the mailing list for other events. There is also, because of this being a learning event, it is eligible for continued development certificate, so feel free to ask for that if you would like it. And we are recording the presentations, including any sort of minor errors as we've just occurred. So here we go. Here I've mentioned that obviously myself, that Silvana's not able to join us directly. She's traveling at the moment, but she will dip in and dip out. But she's our lead on NtTIN. Obviously myself, I've done my introductions, and then you will hear from Jeff and from Steve. And as I say, at the end, we will have a Q&A panel discussion. So just a brief intro, just to remind us, we're really quite determined as a society to regard this not so much as a lot of societies have young professionals. We decided actually it's all about, doesn't matter what stage you're at in your career, is to do with learning more about this particular sector and the technology within it. And it could be that you're an expert in one particular type of technology, but I have actually never known about or understood another. So we're really keen to maintain that as our mantra, NtTIN. First of all, just to get us going, really, we often do hear a lot about sort of cured in place lining, a lot of other technologies like that. People are quite familiar principally in the gravity kind of network area, and there are pressure cured in place lining systems. So that could be a solution, it could be an option, and it is used. But what we wanted to do was give you a taster of a couple of other technologies that have been used for many years and have a decent pedigree. Typically, you're trying to resolve those sort of problems you can see on the screen, and what we're trying to offer to you guys through these events and our other events is the knowledge, the toolkit to understand all the options that you might have available and not be constrained by one particular option. And these techniques we're going to go through have options for supporting for issues with discoloured water, for low pressure, but also for leakage resistance as well. So it's important for you to understand the full breadth of what can be offered. The other thing we always love to do, of course, being who we are, we like to remind people what we're trying to avoid. Quite interesting, I was with a major network operator on Monday, and they are going to be moving into urban areas. They're very concerned about that. And of course, the more urban the area, the more complex the issues of conventional trenching would be. So again, timing's pretty good for this. We're going to explain what you can do and what you can't do with these two technologies. The other thing, you guys are on the call, which is great. You appreciate, well, there must be some value in this. And there's loads of things I could talk about, which I'm not going to do because I could go on forever. But one thing I do want to mention is productivity. With some of the infrastructure programs that we see ahead of us over not 5 years, but 10 years, there is a significant challenge around the sheer volume of what needs to be done. And the guys are going to talk through what, obviously, this technology, but one of the things to keep an eye on is not just the speed of application within a particular length of a pipeline, but also your overall program. Often it's sort of missed. I know works which, if they'd been done conventionally using some of the technology, could have taken a matter of years to do, a couple of years to do. Using this technology, you're going to still need to have access. You're still going to have issues of how you approach the job, but you will still cause some disruption. But you may be causing that for, say, 6 months, not for 2 years. So I think that these two things need to be considered. One, productivity of the physical doing of the work on the pipe itself. How quick is that? And the other bit is your overall program duration. So that's something that we're keen to mention. And then the other thing, I think we get ourselves in a bit of a pickle with this one. I want to mention it. I kind of a bit of a broken record on this now, but are we talking about innovation that's really scary? And frankly, we scare people off, and we're at the cutting edge. And therefore, if you're at the cutting edge of new tech, often, a lot of, engineers are a pretty conservative bunch. We like to know what we're doing. And then we're quite frightened to sort of go ahead. Both the technologies we're going to talk about today have been around for some time. I'll let the speakers explain that to you, and hopefully that'll take some of that nervousness away, and you'll see it as a sort of potential business as usual. So, without further ado, I will invite Jeff to join us. Jeff, do you want to put your camera on? And
hopefully you can hear me as well.
Just have a shout out so we know you can hear him.
Hopefully,
yeah, we can hear.
Yeah, we've got
Jeff. Okay, cool.
Good.
We can hear you.
Now we're going to do a bit of a double act. I'm going to click Jeff's slides and hopefully in the right order. So Jeff, I shall just start off with your first slide and you can just fire away and tell me to move on.
Well, thank you very much. For those of you who know me, that you know I'm not bright enough to speak and operate a laptop at the same time. So Tim's going to run my slides for me, which is most sort of helpful. My presentation this afternoon to you is focused around spray in place or in situ lining. My presentation's primarily focused around drinking water linings today, but we do also produce lining products for wastewater applications, mainly for rising mains. So the process is very similar. Obviously, the sort of products are different to cope with the different environments and everything else. So next slide, please, Tim. Thank you. In situ or spray in place lining, it's a method for applying new coatings inside existing pipes that no longer meet their service level requirements for a variety of reasons. If you talk about spray lining or in situ lining with your older colleagues, most of them will say that they remember in situ lining as non-structural epoxy lining from the 1990s and early 2000s. I'm here today to sort of say, yes, we can still do that, but we've come a long way since that time as well. And we can apply modern coatings as semi and fully structural linings, but more on that later. Next slide, please, Tim. As Tim said right at the start, this is not a new technique. Spray in place lining is not a new technique. You can actually date it back nearly 100 years now to the early 1930s. Primarily, in those days, cement mortar lining was applied. The pipes suffered from encrustation and degradation. The problem is if you just clean iron metallic pipes, within a matter of weeks, you finish up with what was always called red water. You get a rapid reformation of sort of soft internal deposits that sort of run about inside the distribution network, giving everybody discoloured. So you can't just clean them, you have to clean them and you have to apply a sealing coating as well. I mean, obviously, back in the 1920s and 30s, cement mortar sealed the surface and cement mortar lining was used quite extensively up into the 1980s. The cement mortar sealed the surface and provided an alkaline environment for the old iron pipes, passivating against ongoing corrosion. But of course, sort of cement mortar lining applied inside existing pipes gave substantial short-term water quality issues. So the search was on then. So next slide, please, Tim. The search was on then in the 19 sort of, well, I'd say 60s and 70s to find alternative solutions. There were some bitumen linings applied, which is a bit of a sort of leachate sort of nightmare, applying bitumen, and epoxy resins were sort of started to be developed really in the 1970s and gained approval in the 1980s. The additional issue was that if you put cement mortar linings inside old small bore pipes, you tended to reduce the bore even further, and pipes that were sort of sized for Victorian household water demand couldn't carry enough water for modern households with washing machines, dishwashers, everything else. So again, a reason why the industry was looking for thin film coatings. There was really, I suppose, a substantial water quality issue around the UK water industry in the 80s and 90s, and a big push to meet EU drinking water quality directives. So, as I say, epoxy lining became a sort of mandated sort of technique in the early AMP programs. The trouble with it was that you needed 16 hours for the epoxy resin to cure. So by the time you'd cleaned the pipe, lined it, allowed it to cure and put it back in service, the customers were shut off for 36 hours, which is, I'm sure, is something my modern day water industry colleagues could only hope exists instead of the current 3 hours. But as I say, although it was a useful technique, it caused the householders considerable inconvenience. Next slide, please, Tim. So there was quite a push during the 1990s to look at trying to find faster setting materials or rapid setting materials, and the first of these were introduced, obtained Reg 31 4A approval in 1999. The products had a number of advantages. They were more tolerant of adverse conditions. The coatings, because they set rapidly, they weren't subject to so much water damage as was the case with epoxy coatings. And the initial coatings had a 2-hour return to service time, which gave you same-day return to service. Again, also over epoxies, they had superior performance and durability. But again, these were coatings applied at 1 millimeter. But as I say, the main aim of these coatings at that time was to sort of break the back of this 36-hour shutdown that customers had to sort of suffer. So that's the sort of initial sort of background of the industry, and now sort of move on the next slide to talking about why rehabilitation is required. I think the point to stress is that the pipe condition varies from virtually as good as new to completely shot, and there is a complete spectrum of condition of and serviceability in the existing networks. So spray lining, it's not a universal solution for all pipe issues, but it's a tool in the box that can extend the working life of a large percentage of pipes for in excess of 50 years. So next slide, please, Tim. Thank you. So a little bit more about the process. These days we can use the process still as a non-structural barrier coating to clean out internal incrustation and degradation in the pipe, and apply a sealing coat as a thin non-structural lining. A semi-structural pipe, it relies on the residual host pipe strength, but basically the lining is thicker and it can act as a clamped plate over holes and defects that appear through the pipe wall. So quite useful for use on what are termed partially deteriorated pipes. And it's possible to install fully structural pipes, which effectively can be considered standalone pipes that don't rely on the old host pipe in any way. The big advantages of the process is, why would you want to use it? Well, it's a very low or no dig technique really, with minimum excavation volumes compared to other processes. You have small site footprint, so it's easy to work in close-in urban environments. Because the working areas for the lining rig and the sort of launch pit for the lining are very small footprints, this minimises disruption to sort of traffic and other street users. Because it's very low dig and it's minimum disruption, it's a low carbon technique, and fairly typically we would expect a lining rig working around the UK to be able to sort of line something like 600 meters a week. So a lining rig would do your 30 kilometers of network in a year, but that could go up or down. If you're out in the countryside, you could double it. If you're in central London or somewhere like that, you could probably halve it. But the reason it's minimum excavation is because there's no reconnection of service pipes required, so consequently it's very effective. A spray lining applied at 3 millimeter will block a 6 millimeter holes. So since most pipes are since most service pipes are larger than 6 millimeters drilling, it doesn't actually block service pipes. The materials these days, they're rapid setting, so they're allowed for return to service after 1 hour cure. You can start chlorinating after 1 hour, so you can achieve same day return to service. Next slide, please, Tim. Okay, I mean, in the UK, the approvals generally relate to sort of lining non-organic pipes. We don't tend to line PVC pipes because the failure mode is longitudinal split, so you need fully structural linings for that. So probably not the best use of it, but cast iron, spun iron, ductile steel, asbestos cement, and cement or concrete or cement lined pipes. In the UK, we can spray line pipes from 75 millimeters diameter upwards, good old 3-inch pipe. All the linings approved have to be applied in accordance with their conditions of use, which are granted by the DWI, and approved contractors have to be used who comply with water industry specifications. Next slide, please, Tim. Talk a little bit about the actual cleaning process now. A number of cleaning techniques. Main ones in use around the world are what they call rack feed boring, and this is an old sort of illustrative drawing of rack feed boring. Basically, a machine rotates steel rods which have a sort of like a flail set on the head. The flails are driven up the pipe against a flow of water coming from the other end, and they basically bore the internal encrustation out of the pipe. So rack feed borings are a good technique for pipes that have heavy encrustation. If you travel around the world, you'll find that people don't tend to have rack feed borers sort of sat in their yards or anything. So drag scraping, where you can use a couple of winches, is far more common, and as well as pressure jetting. Most countries obviously will be able to undertake those techniques with locally obtained equipment. Abrasive pigging and the vortex of air or air-driven aggregate, really, which is sort of blown through the pipe. The aggregate's blown through to knock the encrustation off the insides of the pipe. Cleaning time, well, that's a sort of function of the level of internal corrosion of the pipe and the diameter. But if the deposits are inside the pipe are light, then a vortex of air machine could clean a pipe length of 100-120 meters in less than an hour. As I said, overseas it's mainly drag scraping or pressure jetting. Next slide, please, Tim. These on the left there, that's the sort of what's called the warhead for the rack feed boring system. They're sprung steel rods that, as I say, are rotated and sort of driven down the pipe on a chuck system, driving steel rods. The deposits from that, obviously, there's quite a big amount of water in that, so the discharge has to go either to a foul sewer or is tankered away to a treatment works. If you're drag scraping or using the vortex of air, whirlwind or tomahawk systems, generally the deposits drawn out, cleaned out are fairly dry, and they can just go to a licensed tin. Next slide, please. Thank you. So, cleaning's required to remove all loose or adhered material resulting from the corrosion process, as per the instructions for use issued by the material manufacturer for the product, and the water industry specification states that after cleaning, the pipe is to be smooth, clean, and free from dust, debris, and standing water. As I say, they're taken from the UK industry spec, which is Water Industry Spec 40201. Our material doesn't require the pipe to be dry because it's extremely difficult to get old mains dry due to leaking joints, water coming back down service connections, etc. But you definitely cannot line pipes through standing water. But some moisture tolerance can be tolerated. Okay, next slide, Tim. Thank you. I hope you could see which one was the before and which one was the after, otherwise I've got a bit of a problem. But anyway, that's kind of like the cleaning spec that we're looking to. It's probably higher than a cured in place line sort of sewer pipe will be cleaned to, because with a lot of these coatings, with non-structural coatings, where possible, you're trying to generate adhesion onto the pipe wall. Next slide. So after you've cleaned the pipe, you carry out a CCTV inspection when you consider the pipe is fully cleaned and immediately before the lining process commences. You're trying to obtain a record of the pipe as it is when you line it. You don't want a CCTV survey from the day before or something like that, because who knows what's happened in that pipe overnight. So CCTV is carried out immediately before the lining process commences. Next slide, please, Tim. And we carry out the CCTV survey to check the quality of the cleaning, highlight any problems. Speed on the clean water side, we go a bit faster than the sewer lining guys. We go up to 10 meters a minute as opposed to their 7. But generally you would stop and view ferrules and fittings. And as I said, it's to check that the final condition of the pipe before you line it. And also you might be able to identify some defects in the pipe that could affect the quality of the finished lining. We also, going slightly out of sequence here, after we've lined the pipe with our material, 15 minutes after the end of the lining, you can examine the pipe ends and CCTV inspect the lining. And the purpose of the post lining inspection is to evaluate the cure, proportioning and mixing of the lining, check nothing's gone wrong during its application, and you can assess the full lining quality. And both of these surveys are recorded and are kept as part of the mandatory sort of lining records that we have. Okay, next slide, please. The actual lining process. The lining process in itself is you will clean the pipe and CCTV it, as we've just discussed. When you're ready, while your cleaning and work is going on, you would precondition your lining rig, and I'll talk about that a little bit more later. But assuming your lining rigs are ready to go and your material components are all up to temperature, you would pull the umbilical lining hose through to the far end of you. So you've got 2 pits. You're working from an open pit to an open pit. You will pull the umbilical hose off the lining rig all the way through to the far end, and basically that umbilical hose, it's got a base pipeline in it, it's got an activator pipeline in it, a compressed air supply line in it to drive your lining head, and it's got some heating hoses. So that's the composition of your hose. As I said, you pull that through to the far end and you will attach a Y block, a static mixer, and the lining head at the far end, because you only want to mix these components right at the very end of the system, really. So you will then start pumping material. You have a spin-up stabilization period in the open trench at the far end, and then basically you would start winching back the umbilical hose, which pulls the attached spray head with it, and you will then spray your coating centrifugally onto the pipe wall, and the pumping rate that you have combined with the rate of pullback gives you the lining thickness that you achieve. That's the sort of basic process. You will look.
Oh, Jeff, you've just gone on to mute for some reason. I'm not sure what's happened there, but you're muted.
Thank you. Am I
There
back?
you go. We've got you back now.
Oh, I didn't touch anything, I promise. But anyway, there we are. Yeah, so that's the basic sort of spray process. We have some views of the actual sort of lining rig now. So next slide, please, Tim. These are the side views. So looking at the left-hand upper picture, you can see the sort of two material tanks there. One contains base, one contains activator. At the front, a yellow item, that's a generator which powers the heating system and the rig propulsion. On the upper right-hand picture, the other side of the lining rig, at the left-hand end of the rig, you can see the metering pump. So that has three legs on it, so it's fixed ratio delivery. So there are generally two base pump legs and one activator pump leg. So that's fixed ratio displacement of material at the correct mix ratio. Next to the tanks, the material runs through flow meters, and from the flow meters it then runs through a central coupling into the hose drum, which is inside at the sort of at the right hand end of the rig. I draw your attention also to the computer sort of panel there. That part will produce a printout for you showing all the lining parameters, so you can see all the mix ratio, lining pressures, lining thickness, pumping rate, speed, etc. on a printout there. The lower picture there on top of that red compressor, that's a lining head assembly. So working from the left hand side, you have two material component hoses, the base and the activator, coming into a Y block. There is then a static mixer hose in the middle, laying over that yellow tape on the compressor. From the static mixer, the material is discharged through the middle of the air motor at the end there on skids and into the lining cone, from which it is flung out onto the pipe wall. Next slide, please. That's the other side view of the rig. So again, working from the left, you have the air-driven pump, which is the sort of material main metering pump for the material. The tanks, there's an air dryer shown there because we have dry air on top of the material. You can see the flow meters there, and as I say, there's sort of central coupling on the hose drum there, and the printer mechanism for the control panel, the computer control panel. Next picture, please, which is just the end view. You can see the umbilical lining hose there on its drum. That is pulled out through the lay-on mechanism at the back there. So there's different sizes and lengths for different sort of mains applications. I mean, fairly typically for small bore pipe work, the diameter of the umbilical hose is about 65 millimeters, and the length of the umbilical is generally something like 170, 180 meters. The computer screen on the left there, that's the operator station. So the operator has all the rig parameters on display for him during the actual lining work. So that's the type of equipment that is used. There are various innovations on the equipment. Recently we have auto start, so you don't have to have people down in the excavations to either launch or retrieve the lining head anymore. Next slide, please, Tim. Generally, the Drinking Water Inspectorate mandate what information needs to be recorded during a lining, which are these sort of 7 parameters there that you see: time, distance, the material base and activator pressures, the mix ratio. If you know the pump flow rate and you know the pipe diameter and the speed that you're pulling it back, you know the coating thickness, because you have a volume divided by an area, which will give you a thickness. So that gives you the lining thickness that you have. It's possible these days to have modem connection on the lining rig, so the lining information can be seen live by the client, either on a phone or on a laptop back in the sort of main head office. The lining rig, it's important to stress, has full QA control of the process. It's a sequential control system, but it will shut down on critical lining parameters such as mix ratio. If the lining rig runs out of mix ratio, if it goes at more than 5% out for 2 readings, it will sound an alarm. If the mix ratio goes more than 10% out for any moment, the lining rig will shut down automatically. The key part of this equipment is to make sure that water quality is protected at all times from the material, and that you do not finish up with incorrectly mixed material inside drinking water pipelines. That's also another function of the CCTV survey, is to sort of check, mix, cure, key factors like that. So that's the lining equipment, as I say, which must be operated by approved contractors. There's a UK approval system with a nominated certifying body, which is WRC. And all the staff, all the crew members on the lining team have to be trained and reassessed every 3 years. So if we move on now to material features and benefits, I mean, talking a little bit about our material here, it's what we call a 3rd generation aliphatic isocyanate based polyurea material. Probably doesn't mean a lot to most people, but it does to sort of nerds like me in the industry. We have a range of international approvals for water mains from 75 millimeters upwards in the UK. We have NSF 61, AS/NZS 4020 for Australia and New Zealand. With a French ACS approval, we've an Italian approval, SS 375 Singapore approval, various others. This polyurea product, it's of a family of lining materials that's been used and trusted by water companies around the world for over 20 years. It's been developed to be easy to pump and apply. It's moisture tolerant, which we think is an essential requirement for renovating aged water pipelines. You know, you're not in a factory environment here. You are always dealing with the potential of water ingress into what you're trying to line. The material is BPA and VOC free. It is also free from PFOS and PFOA as well. It's surprising how many times we get asked that around the world. It's been formulated to be a low exotherm product, so it avoids shrinkage during product cure. And we utilize some novel technology in the material to minimize water absorption during service, because water absorption is what kills linings. If you get water absorption, you get swelling of the product, you get debonding, you get a shorter service life. So this is specifically formulated to avoid moisture absorption. So consequently, we have a high wet creep rupture strength, which is what you need for long-term pressure containment ability. And we have a high long-term wet flexural strength, which is what you need to resist collapse under vacuum or external pressure conditions. In the UK, we can apply our material from 1 millimetre up to 3 millimetres thickness per lining pass, with a maximum lining thickness on our Reg 31 of 9 millimetres. The products touch dry after about 90 seconds. You can CCTV and review your homework after 15 minutes, and you can commence return to service, which is generally spray chlorination after 1 hour. So we have found in Yorkshire over 2022-23 that it is possible to complete linings within the 3-hour shutdown period, provided there's not too much cleaning required on the host pipe. Our material's got excellent intercoat adhesion, so you can put your multiple pass linings in. If you overline it within 6 hours, you can't find the join. Anybody who designs sewer linings for a living will know that 2 times 3 doesn't equal 6, because, you know, 2 3 millimetre coatings, separate coatings, like onion skins, like layers in an onion, it's not as strong as a single bonded layer. So yes, we can achieve sort of seamless lining applications, and we can design linings using ASTM F121616, which the cured in place guys amongst you will know that's the design standard used for designing CIPP linings, but the equations in Appendix X1 also work for spray linings as well. Next coat as well, slide, thank you. Okay, so this, I've got these couple of slides in because around the world generally you find that most material manufacturers will quote you the dry properties of their lining material, and we sort of turn around and say there's not a lot of use in knowing the dry properties of a material that's intended as the lining of a drinking water pipe. It's going to be dry for about an hour, and then it's going to spend the next 50 odd years in a fully submerged environment. So the dry properties aren't that relevant, but this shows the evolution of this type of product over time. So here we compare the sort of properties against the 3M SK2400 product, which most water companies consider to be quite a good product and a sort of benchmark for sort of lining materials. So just very quickly look at the tensile strength that break at the top there. Our material, the value is 45.5 MPa dry. The Scotch coat figures 35. So if we move to the next slide, please, Tim, you'll see the tensile strength for the fully saturated material. Well, ours has gone from 45.5 to 41.5, but the Scotch Coat 3M product has gone from 35 down to 26. So you can see the effect of just saturating the material. And this is short-term figures. You know, you would get these results in about a month, you know, let alone sort of 30, 40, 50 years. So that's the dry properties. So what that translates down to is the bottom two rows on that chart show the projected 50-year tensile creep rupture strength, which is needed for fully structural linings, and the projected 50-year flexural creep rupture strength, which is what you need for covering holes in partially deteriorated pipes. And basically, in both of those slides, you can see that the Resiline values are more or less about double what they are on the second generation 3M material. So what does that mean? It means that if you're designing linings for pipelines, a Resiline 320 lining is roughly half the thickness of what a 3M lining would have had to have been. So that's how much the sort of, you know, the evolution of the technology has sort of moved on over, you know, over the past sort of 10, 15 years. Okay, so as that say there, this is an engineered lining product to extend the working lives of aging pipelines. So next slide, please, Tim. So how are these materials used? Well, this is back to the original sort of Section 19 non-structural sort of lining sort of works that were undertaken in the UK. And as I say, there was over 30,000 kilometres of pipes epoxy lined in the 1990s and early 2000s. But the problems for non-structural linings, they're still common around lots of parts of the world. The water is discoloured. There are biofilm issues in pipes affecting water quality. There's a very high chlorine demand, so there's no chlorine at the end of the distribution network because it's all been soaked out by these sort of iron deposits in the pipes. There's hydraulic issues because you've got loss of pressure and loss of flow from all this build-up of all this internal pipe sort of corrosion inside pipes. So if the host pipe is relatively sound, then basically you need to remove those internal deposits and spray a non-structural or an EN 11295 Class D lining through the pipeline. Next slide, please, Tim.
I'll just give you a 5-minute warning, Jeff.
Okay, yeah.
Oh, no, it's not behaving.
No.
Slide bit, yeah.
Yeah. Can I have another 10 seconds for that, Tim? Okay, so anyway, so for these, the host pipe needs to be in fundamentally structurally sound condition. Applied where the original factory coatings have deteriorated. I think I've just run through all of that really, but lining thicknesses would generally run in the range of 1 millimetre up to 2 millimetre, depending on the host pipe diameter. So the product can be used to apply non-structural protective coatings. Moving on to the next slide, Tim, please. Here we are. Not all pipes are in fundamentally sound conditions. You've got this vast amount of pipework in the sort of grey area in the middle, where they're what AWWA would term partially deteriorated pipes. There's still fundamentally good residual strength in the actual pipe wall, but it's not hydraulically sound. It's got leaks on it. It's subject to failure. You've got holes rotting through the pipe wall, and in those conditions, this is really probably the sweet spot for spray lining. you want to apply a semi-structural lining. So Class B semi-structural lining is an adhered lining, which is generally used in larger diameter pipes. Class C semi-structural linings, they're standalone linings which are not dependent on adhesion to the host pipe wall, where the lining, the hoop lining that you've applied has sufficient hoop strength to resist vacuum or external groundwater pressures on the lining. And these linings are fundamentally installed to bridge holes and defects that appear through the pipe wall, and relatively thin linings can withstand quite large corrosion holes behind them. The lining acts as a clamped plate. Something like a 3mm lining can quite happily resist sort of up to sort of 8-10 bar sort of operating pressure. So this semi-structural lining is, as I said, it's the sweet spot probably for spray lining. It's around the world, it seems to sort of work out about half the cost of replacement or other sort of fully structural techniques. Next slide, please, Tim. Finally, oh, sorry, this is the semi-structural linings. As I say, capable of bridging holes or cracks in pipe walls, so they reduce leakage. They can increase the supply reliability and resilience. Generally, the linings are about 2.5mm and upwards, depending on the pipe pressure. 20 kilometres, in excess of 20 kilometres of drinking water network was renovated in Yorkshire Water, with 85% of that work undertaken within a 3-hour shutdown. So it is possible to achieve that. As I say, that's extending the life of a partially deteriorated pipe. Next slide, please, Tim. Fully structural linings. There are 3 requirements. It has to have sufficient long-term creep rupture strength to contain the maximum allowable operating pressure and be capable of short-term hoop strength to resist vacuum or surge loading. We can generally meet those first 2 conditions. The failure mode of many host pipes doesn't cause significant dynamic or energy release effects. So for ductile iron, steel and PVC pipelines, yes, we can put fully structural linings in. We wouldn't make that claim for cast iron pipelines because the failure mode tends to make the lining fail as well. But ductile steel and PVC we're okay with. Lining thicknesses would generally be from 5mm up to our maximum of 9mm. But we would say we don't really tend to sort of look at that too much, because you probably find it's cheaper to lay a new pipe than put sort of 9mm or our NSF approvals up to 14mm. It's not really probably cost effective. You're moving out of where we can sort of really compete against other techniques if you want to put fully structural linings in. Next slide, please.
There you go.
Yeah, okay.
A minute to wrap up here. This is your last but one, yeah?
It is indeed. Cool. Okay, so why isn't there a lot of lining going on in the UK? Well, the issue is the way in which Ofwat have set out the finances in AMP8, where the price control deliverables are basically given for replacement of mains and not their refurbishment. As a lot of you will know, Ofwat have stated they consider the life of a new PE pipe is up to 150 years. So we don't currently qualify as a replacement pipe, although we are undertaking some work to try and change that. But so in situ lining can be used under water quality and leakage reduction programs, but it's not an alternative to mains replacement. And the other fundamental issue that we have at the moment is this 3-hour customer lost minutes shutdown period. If you start putting higher build linings on, or sort of higher build renovation techniques, you've got to start reconnecting service pipes, and that's generally impossible in a 3-hour window. So what the water industry needs to convince Ofwat to change the current financing regime and operating regime to allow more use of trenchless technologies is probably sort of sums up my sort of statements for that. I'm sure Steve will have more to say on that as well later. My last slide, that shows a lining, a 3mm lining applied inside 150 steel pipe, which was undertaken 2 years ago in mainland Europe. So we're sort of active around a lot of parts of the world. Currently not active in the UK, but we hope that will be able to change. That's me done, Tim.
Jeff, thanks very much. Okay, I shall endeavour to escape from that, come back in the room, as they say. Just bear with me. I'll stop sharing, and then I'll stick my camera back on if I can find it. There we go. Okay, thanks, Jeff. Let me just have a look where the chat is. I think we had one question drop in. We'll just pick up one question now. Oh, we've got a few coming in there. If we can just pick up one, and then we'll endeavour to go back to these on the panel at the end, if that's okay, because we need to get Steve on to go through his stuff. But if we just pick up that one, I think it's the first one as I can see. Let me just have a look, which is about asbestos cement. Is this a kind of appropriate refurb sort of system for asbestos cement? Do you want to comment on that? But it says lined with cement already.
Lined with cement. Oh wow, that's yeah, okay, yeah. I mean, yes, that would be a suitable application. We line a lot of asbestos pipes around the world, certainly over 20 kilometers in the last year, primarily in 6-inch diameter pipes. Generally, the problem with asbestos pipes is softening of the pipe wall. And if you internally spray line them, then you will seal that surface and prevent further deterioration of the host pipe. So yeah, it's a very valid technique for that. I would say if it's got a cement mortar lining in it, that would still be porous to some extent. So yeah, so applying a coating over that could potentially still have value.
Okay, and I think we will pick up this other one, but the other ones are really more information that people are putting forward. The last one was auto shutdown. Does the job need to be restarted? I think the thing there, do you start from scratch, or can you re-kick the system? What would you do if you were sort of, I guess, halfway through a lining and the machine shut itself down?
Yeah, well, I mean, firstly, you would retrieve your lining equipment out of the pipe, and you would conduct a CCTV survey to find out what you've got there. Assuming you had no unmixed material present in the pipe where it shut itself down, which is possible these days with the auto shut off valve that we have, you've got two options. Then you can either resolve the problem that caused the shutdown, pull the hose all the way back through to the start, overline what you've done, and sort of carry on through to the end, or you would have the alternative option to excavate at the end of the good lining, cut out, and start a new lining from that point. Generally, I think you'd find the quickest option is just to overline the thing from the far end again, pull it all back through and overline.
That's because you've got, just again to reinforce for people less familiar, that's because it's a thin lining in the first place anyway. So you're not actually putting that thicker a lining on.
Well, you could overline a semi-structural lining if you had a 3mm lining, for instance. You could overline that again up to 6mm, so quite happily. And so one part of it would be more semi-structural than the sort of second half of it, which would just be back at 3mm.
Okay, thanks for that. All right, I think we'll move on. We're pretty well bang on 3 o'clock, so I'll invite Steve to join us if you want to stick your camera on. I think you're going to do the magic this time, Steve, so and share your screen. So we'll let you do that, and then we'll obviously make sure you know that's all working, and then let you go through your presentation.
Can you see that, Tim?
We can see that. Yeah, if you put it into
slide mode,
play mode, launch it, and then we'll be good. That's it. We're good. Thanks, Steve. I'll let you fire away.
Okay, I'm going to talk about, our business is called DieDraw. That'll be quite self-explanatory from these slides. But what I'm really going to talk about is polyethylene, and particularly PE100 lining. And before we talk about our specific technique, I'll give an overview of all the different techniques that use PE as a principal lining material. Why do you want to use polyethylene? It's got the PE100 in particular has got the best track record probably of any material in these industries, particularly in low pressure water and gas applications. It's been very successful now for more than 45 years. Approvals around the world. It's Reg 31 approved. Different PE100 resins are all Reg 31 approved in the UK. It's kind of superseded P80, which is used more extensively really in the gas market. Essentially P100 really is the go-to material these days. You have a fully weldable thermoplastic with a continuous system, so you haven't got any joints. It's a very highly ductile material. It's got good strength and impact resistance. And it's also as well as being used very very frequently and very reliably, with a very long lifetime prediction in the for open cut and traditional installation methods. It's also got a very successful track record with installation, no dig installation technologies. It's got very good availability. It's very highly specified. The British standards, the EN, ISO, ASTM, all around the world. The specifications are very robust, and it's got a design flexibility. So I think one of our key drivers is really everywhere defaults to high pressure pipelines such as SDR11 for 16 bar pipes or SDR17 for 10 bar pipes. Quite often these are over specified by the clients, which means that we end up with perhaps something that's operating at 4 bar and it's got an SDR11 16 bar pipe. This is in our view, this is wasteful of material, and you're also reducing the flow capacity of your system. And I think that we need to get more into a thinking of using the specifications as they stand to try and specify the thinnest PE pipes possible, because of all the environmental and cost advantages to those. The product now, really, the PE100 product is 100% recyclable. So this really has it's transformed the industry. This material, the contractors love it, the installers love it, and the clients love it, because the failure rates are really extremely low, as long as welding is done to the required standards. Now, I'll just take you through what these are these come from the International Society for Trenchless Technology. I used some of these on a presentation to them a couple of months ago. And these old thumbnail drawings they have on their website, you should go to it. It's very good. It's very, very informative for all the different techniques that can be used as for no dig installation. Slip lining is really the simplest process for getting a PE pipe inside a deteriorating It can be anything actually. It can be it can be GRP, it can be cementitious pipe, it can be a cast iron pipe, ductile iron pipe. I appreciate Jeff has focused very well on the cleaning and the scraping and the preparation. All that is required for all these techniques using polyethylene pipe as well, and it's a very important part of the process. We need to make sure that all that tuberculation and anything else that's in there is removed thoroughly before we line with the polyethylene pipe. Slip lining is the simplest method of inserting a polyethylene pipe inside a hose pipe, and it's really quite widely used around the world. The drawback of it is that you've got to put a pipe in that's significantly smaller than the pipe it's going into. So you're dramatically reducing the flow capacity of the pipeline. But where that's acceptable, it's a very good and very well proven and simple technique. Now, what we have, and I'll talk about this on a later slide. It's termed as swage lining on the ISTT website. Prefer to use the more strictly correct term, really, which is dye reduction. This is the process we use in our company, Dye Draw. It's a tight fit liner. We can also use it as a close fit liner. I'll come on to that. And it can be either fully structural, semi-structural. It's used for a large variety of applications. We're talking about water, wastewater and gas. It's also been extensively used in subsea water injection applications and also for mining slurries. So it's very well established around the world. It's a very versatile technology, and what you can see on that cross section is there. It is possible using this technology to put an absolutely tight PE pipe inside another the hose pipe, thereby really maximising the bore of the hose pipe. And I'll show you our. Go back to it. Sorry. I'm pressing the wrong button. There we go. This is an animation we have on our website, which just really quickly shows how the process works. So we weld up a long string of PE pipe with a towing head there, fully rated, solid towing head, and we're pulling it. The pipe is originally larger than the outside diameter is larger than the inside diameter of the hose pipe. We pull it through a reduction die and into the hose pipe under elastic tension. It comes out the other side and we just simply let it go. And the elasticity in the pipe reverts to produce a tight fit in the hose pipe. Very simple when you see it all done like that. There's a bit of engineering that goes into it, a bit of clever engineering, which gives us our flexibility in design. But it really a simple and straightforward process, and I'll come on to this. It's really been, in my view, very underexploited. It was used very extensively in the past and has not been used so much recently. British Gas did thousands of kilometres using this technique, largely with PE80 in the 1990s. Whilst I'm mentioning Dye Draw, I appreciate we've got Radius Subterra in the audience somewhere. There's another technique called roller reduction, and that is very similar to the dye reduction process. And just make you aware that process is also available. There's also a fourth type of liner, which is a folded liner. Again, Radius Subterra, that is their technology, where you fold a liner and you place the folded liner inside the hose pipe, and then you pressurize it to revert the liner to a tight fit inside the hose pipe. Now, getting back to die drawing, this may be a new process to many of you. It isn't at all. It's been around for a very, very long time. It's been around since the late 1980s. In the mid-80s, British Gas came up with this technology called swage lining. And when they initially introduced it, they were heating the pipe, or trying to heat the pipe while they were installing it. And this great big heating apparatus was rather cumbersome and very difficult to control in a site situation. I mean, one of the beauties of using inert thermoplastic polyethylene is it's factory produced and turns up on the site ready to go. And what was found, I worked for the company that developed this for Northwest Water, and British Gas came to the same conclusion at the same time, that actually you didn't need to heat. So at the time, the two, British Gas and Northwest Water, who became United Utilities, of course, had competing patents, and then and it was being used in both the gas and the water. There was a bit of a bum fight about it, and they came to an amicable agreement and licensed the technology of swage lining under British Gas by the technology company Advantica, that was part of the British Gas group. From that point on, there was still quite extensive amount of lining done in the UK water industry, particularly with United Utilities, but also several of the others used it quite extensively. British Gas went kind of mad with it. A very large proportion of their network was lined using the swage lining in the 1990s, and very effectively too. Those pipelines have got a very good track record. We don't really hear of problems with any kind of failures or anything of that technology coming back to bite us these days. So it was very successful. It sort of petered out as British Gas had done what they needed to do. And the water industry, I felt, were a little bit. It sort of got a name as a gas technology, and really stopped being used in the water industry, where it had been known as die drawing. It was obviously swage lining. British Gas, Advantica held the intellectual property rights, and as the technology was getting used less, and another reason for the technology getting used less had been some of there is a bit of engineering involved in this, and without proper understanding of the behaviour of the polyethylene under these loads, and the sizing of the die, and the safety factors, and the handling of the equipment to install these liners, it was just being used a little bit less frequently. And in Northwest Water, United Utilities, the decision had really been taken to sort of abandon it, and they moved on to slip lining. But obviously, slip lining sort of has this drawback of not being able to offer the flow capacity that die drawing can. By sort of 2009, I was at this company called Swage Lining Limited, who bought what was left of the technology from Advantica, who had also been licensing the technology quite successfully around the world. And at Swage Lining, I was privy to all the extensive testing work that had been done by both the water and British Gas by under by Northwest Water and British Gas, and there were various softwares to design this this lining that were available, and I sort of kind of saw the flaws in both systems and improve the software so that it not only took into account the viscoelastic properties of the thermoplastic polyethylene, but also was considering the loads and the restraints required when you're installing over what can be quite considerable lengths. In 2016, the technology was sold to Subsea 7. I stayed in Subsea 7 for a couple of years, and we'd been lining water injection lines in the North Sea very successfully. Very exciting technology and very interesting to use, but obviously the North Sea is not doing that as much now, and particularly with the current government. We had been looking at the utility market. I saw an opportunity to set up on my own and look at the utility market, particularly in the UK, where I felt the technology had been underexploited. And we set up this company, Didraw, in 2018, and we've been gradually getting projects, not just in the UK, but also in Scandinavia, and we're looking at others around the world. And really trying to bring it back into the water industry, where I believe it truly belongs and was never really used to the extent it could have been. So it's got a very long history. It's been used over a very wide range of applications, and the understanding I've got since reintroducing it is actually it's largely been something that's been forgotten about. And it is, a really exciting technology. It really you can really replace a pipe by putting a new pipe, a PE pipe inside it. So I appreciate Jeff covered some of this, which was, there are different types of liners. So we've got a fully structural liner. This is where we're putting something, a pipe in where it's got the full pressure rating of the hose pipe. All slip liners are fully structural liners. They tend to be thicker because they need to be fully pressure rated for the application. This is where pipes are in really bad condition, and really there is no reliable structural strength of the hose pipe going forward. Another type of liner is obviously an interactive or a semi-structural liner, where we're utilising the hoop strength of the hose pipe, and we can justify a thinner liner than the pressure rating. For example, we use an SDR 51 in Stockholm, operating at 10 bar. There is a methodology that exists where we can determine the strength of the pipe for bridging holes over 50 or 100-year lifetime. So the approach is we go to the water company and say, this pipe could withstand, say, 150 millimeter diameter hole in 100 years' time, if we're putting in something that's less than the pressure rating. So there's a very effective methodology there. So I like to do these visual things. I've included less of the very techie stuff in this slide quite deliberately, but the traditional slip liners, and these are some of the typical SDRs that we'd be using. This is the impression of what it gives you. So it is quite a substantial reduction in flow capacity, but where that's acceptable, it's a very good solution. Now, these are what I call close fit or liners, where in the water industry, most frequently we will have a close fit liner rather than the tight fit liner. The reason for this is we will be using a specified polyethylene pipe size. And for example, we might be putting a 280 pipe in a 3 or a 315 pipe in a 300. If you put in a 315 pipe and we get a tight fit, if you put a 280 and you're going to get a slightly close, you're going to get a close fit instead. And this is because obviously there's the standard pipe sizes, but what is actually available and what we can do, and this is what we did for the subsea water injection lines, was you can actually these days. It's not. You can get certainly in on the continent. We can get Reg 31 approved pipes that where we can induce a tight fit by designing a pipe that is an unusual size. So if for example, if the pipe was I'll give a subsea example. It might be a 250 millimeter ID steel pipeline. This could be operating at 250 bar on a water injection line, and we typically design something like we procure a PE pipe with a 265 millimeter OD pipe, so that when we reduced it down, we could get it inside the hose pipe, and then when we release the tension on it, it's tight inside the hose pipe. So it is possible to get absolutely fully tight fit PE liners. But even our even our close fit liner is a huge improvement over a traditional slip liner. So really, this is what we're saying. We're saying we can have full replacement within the hose pipe. Of course, we got off watt and 3 hours, which makes that quite challenging. You know, we at the moment we really need pipes to be abandoned or a bypass put in. But in principle, we can do this, and we have very quick installation rates when everything is prepared. So to get a pipeline on and off in 3 hours is not really plausible, but it could be done in a relatively short space of time. So I think if we could. Always what people like to see is some case studies, and these are the case studies we've been using for a couple of years now, but these give a good spread of the type of pipelines that we can do. So we've got both potable water and wastewater examples. We've got some semi-structural liners. I say the Stockholm project in 2021, we put a 1045 millimeter non-standard pipe, as I've just been explaining. We put an SDR 51 in a 1000 millimeter steel pipeline as a liner, and you know, a low-rated pipe can operate at 10 bar under those circumstances. We did all the design work to show what gaps could be spanned and holes could be bridged and all this kind of thing. So but what is perhaps more common and has been certainly common in the UK recently is we've been doing these fully structural close fit pipelines where, for example, the Seven Sisters projects in London, where we were installing 900 millimeter pipe in a 914 or 36 inch 1850s cast iron pipe. On that particular project, the largest slip liner that could be installed would be 800 millimeter, and by us installing a 900 millimeter pipe, we could achieve the flow capacities that were desired. So it really is, you know, quite effective and quite useful, and we can do it in we can do it in these highly urban environments, which was something that is having developed the technology now. We've done another 10 years of development of the technology, and when we moved from when we set up die drawing, the two issues that had been needed to be overcome was understanding the navigation of bends and the loads and the limits and how far we can go going around bends. And the other thing was really to improve the temporary works with proper rated temporary works. Compared with perhaps the way it had been done in the 1990s, where winches had been strapped to things without real proper appreciation of kind of the forces involved. Another example, and I'll show a little bit more on these two examples: the Seven Sisters in London, large potable water, and we've got this the sewer rising main we did for Angling in 2024. So I believe some of PSS are on the call, and thanks to them, we did this in collaboration with them. But sewer rising mains an ideal application for this technology. We put a fully structural pipe in there, an SDR26 in a 18-inch pipeline. So this is just some nice pictures showing what we're doing in London. It was quite impressive. There you see the towing head, and we're stringing out several hundred meters of pipe along Seven Sisters Road. And this was the initial part of the initial phase of the project. We used an SDR21, which was required for the traffic loading. But we had to devise and design some quite interesting equipment so that we could pull the pipe from a side road. And you see we came up with this winch system, so all the load was transferred out of the pit and didn't risk or jeopardize the two adjacent mains. There was very little space because it's three mains in parallel there, and we had to get the successfully manage these loads into the pit without disturbing the adjacent mains. And we carried on to do much more of this, and in a couple more phases of the project, where again you can see we use some pretty spectacular and interesting equipment in order to install this. But we did find the space in central London. This had been something where we would only perceive that you could do pipes of this size really in a rural location such as the Burnley Aqueduct for United Utilities. Now, I'd just like to show you this because I want to show that really the technology really has advanced from that was being done in the 1990s. The best that could be done in the past was what we're doing here. We'll look at a profile of the pipeline, and we would just be measuring the angles between any deflections or bends in the pipeline would be measured, and these would be put into our software. So we'd say there's a bend at 100 meters, and we'll put that angle in to determine the value of the loads throughout the installation, and that also drives the design and the size of the liner that we want, which can be adjusted by selecting a different die for the project. So what we got here is actually this is snapshots of the LiDAR survey that we did on this Seven Sisters project. So I think there were 2 billion data points on this. So these are snapshots every metre and a half throughout the entire pipeline, and there you can see the red is really the tolerance that we want to be lining at, and this is the anything within the red line we'd have to remove. As I say about the Ofwat 3-hour rule, while there are a lot of challenges in a place like London, the fact that the network is so extensive means that they would just divert the flows to other parts of the system in an extensive urban environment, giving us the time to do the project thoroughly. And as you can see, you fly through. and we inputted the data from the LiDAR directly into our software, and we can now predict the exact loads going around bends when we're inserting a pipeline in. This is really new technology. I don't believe anybody else is successfully doing this. So when we installed, obviously polyethylene is temperature sensitive, so these loads change with temperature. But we knew exactly our design load prediction was within 1% throughout the pull. So all our insertion is very predictable, and there is no guesswork involved. When we say we can get a pipeline in, we can definitely get it in. Go back just a minute. That's it, right? So that's a large diameter pipe, and then a more of a medium size, and another application, sewer rising main. Polyethylene's ideally suited to this application. My thesis 25 years ago led to the water industry information and guidance note for using polyethylene in this application, and a large number of sewer rising mains were made in polyethylene from that time onwards, and we hear of a few, if any, problems in those. Again, the successful track record of polyethylene. Here we've got a 1980s ductile iron, very severely corroded. In fact, it was almost full of holes, I think you could fairly say, and it had flooded. There'd been some flooding of a farmer's field. We needed to get things back on very quickly. We worked together with PSS on this. They did a good job to get things moving, and we managed to get back the farm in time for him to harvest his crops. It really is an ideal solution for this application. Polyethylene is very resistant to the fluctuations in repeated surge events and fatigue loading. So you can it's only operating at 2 bar. That you like to get pressure fluctuations in pump sewerage applications that are double that, but a 6 bar pipe, even a 2 bar rated pipe would be, according to the guidance note, acceptable. So polyethylene is so resistant to those what essentially are overloads, that you can, if you had fluctuations of a 20 bar in a 10 bar system, you could still use a 10 bar pipe, because the polyethylene responds to those sporadic overloads rather than it can cope with those transient pressures. So in this case, we're putting in SDR26. The pipeline length is 1,067 meters. We've successfully pulled 1,500 meters with this technology. We believe you can do a lot more. We've just put a patent application in which suggests we can go a lot further than that. But obviously, the limitation on that is that you have to string the pipe out, and of course you can see before we cleaned it, I'm afraid, on that picture, but you could see how far we have to string the pipe out, and luckily, being in a farmer's field, it was an ideal location for that. We could have pulled the 1,067 in one go, but it was actually more sensible to go in the middle and pull 500 meters either way, so that we weren't interfering with any more of the farmers' activities. And we pulled, and I think that there's a couple of really good takeoffs from this. Actually, we still had to go through 22.5 degree bends. We barely noticed them. It really easily goes through 22.5 degrees, and it's actually been through 45 degrees with an SDR11 in the past, this technology. But the point is, we actually understand the loadings when we're going through these kinds of bends. We achieved 2 insertions of over 500 meters, and I think the 567 meter insertion we installed in 3 hours. There's a lot of preparation and there's quite a bit of engineering goes into that. We've now got this kind of equipment. It's very simple that you can just drop in the pit. We don't need the big reinforced concrete that we needed in Seven Sisters in London. And it's a relatively simple process once it's all set up. So what the attributes of die draw, and most of these things are also relevant to the other PE lining techniques. It's an established low-cost replacement, I think is the word, process. It's not refurbishment, it is actually replacement, because the smoothness of polyethylene means that even an SDR17 going inside an old ductile iron main, the reduction in bore is more than offset by the smoothness, so that you actually have a greater flow capacity. So anything SDR17 or thinner will have if it's a tight fit, will have a greater flow, a better flow capacity than the original pipe. Significant savings. The figure I'll put an approximate on this, and I'm being a bit conservative, but we believe we're about 20% of the cost of open cut. So I've said 20 to 25% of the cost of open cut. And I was a bit surprised about this, but on the case studies I've seen recently, we seem to be lower cost overall than cured in place linings, particularly because we can pull very long lengths, installation lengths in one go. We've got a 100-year design life. We've got all the good things about P100. Very little reduction. We do need a couple of pits. It's a very low carbon footprint compared with open cut. And we can install extremely long lengths, and we're working on even increasing that. They were very important in the subsea market because we needed to install. We installed a water injection line once in 2.5 hours, 1,500 meters. So you can really go at 10 meters a minute if the conditions are correct. Obviously, it's Reg 31 compliant, and it's a natural process. We don't need to cure or post-pressurize. We can have an independent, fully structural, and we've got modelling techniques that really enable us to go through the bends. And we've actually developed that further, because the limit with LiDAR had been that you cannot get the equipment in a pipe that's less than about 500 millimeters. I think we've found a way around that now, and we're using a laser system that can actually get us the data so that we can plot out and map the interior of the pipe at the same time as the camera inspection process, so that we can use that data to input into our software and then adjust our die design, which is a very flexible design. Because we can get a die made in a couple of days, and we'll just change the size of that die to reflect the interior geometry of the pipe and ensure the loads that we're going to get around those bends. So that's me. I'm hoping there's some people in the audience who actually remember this technology. It's been a little bit of a surprise that it's been forgotten, but we can assure you this technology has now been around for the best part of 50 years.
Thanks, Dee, for that. Really appreciate it. I know there's a lot for people to take in. I do think it's really important to demonstrate that pedigree, as Jeff has, with the sort of history and development of the spray lining technology. And you gave a good overview of that kind of subtle difference between slip lining and other close fit linings, and then ultimately tight fit lining. So that was very useful. What I'll do is just one question for you, then we'll open out for more of a panel discussion, and we'll pick up some of the questions. But in fairness to the same question that Jeff had, if you had an asbestos cement main and it was cement lined, I think I know the answer, but what would be the answer? Can you do that?
Yes.
Okay.
Is that a simple one? Yes. I think we can go through most most pipe materials, so long as again, I really emphasised. I thought it was very good. Was Jeff's bit on the cleaning and the scraping and the pigging and the preparation. Obviously, it's critically important if you're putting a resin liner on there, but it's still very important for us. The thing that would really tends to be the biggest issue would be when the pipe gets very oval. So ovality is the thing. We've seen it quite recently on a number of PVC pipelines. But in theory, we can line a PVC pipeline, but if the ovality is, say, greater than 25%, and then we're going to have to put a very small liner in, which isn't going to be appropriate. But any pipeline, we need to clean what's in there. We need to know what's in there. We might. Quite often, we particularly cast and ductile, you find repairs in there where the pipe is actually of smaller diameter and they don't know about the repair. So, a thorough inspection to determine exactly what's there. GRP pipelines and cementitious pipelines, you've got to worry about anything that's delaminated and make sure all the debris is removed. But essentially, we can go in anything.
Jeff, can I ask you if you are still online, if you can stick your camera on? I can see you there, so hopefully you're still with us. If you want to rejoin us, Jeff. Hi.
Yes.
So what I'll open it up now. I've got one or two other questions to kind of help get this going from a general panel point of view. We've got one or two. Again, I think people have put in the fact that there are other close fit lining techniques. Steve, from our point of view, KSTT, the more the gospel is spoken about, this is an alternative to relaying a pipe. That's the key bit. We know there's other technology available for new installation and other things, but really, it's good that people are actually mentioning other processes, I think, and the use of polyethylene. With this technology, I think it can be confusing people. You're doing an online sort of semi-structural or fully structural solution. I'm going to open up to you both. You kind of, what would be the sweet spot? What sort of project would you wouldn't even have to almost assess it. You would just go, yep, but that's absolutely within the diameter range and the type of project that we think this system gives value. If I can start with you, Jeff. I know that we could do all sorts of things, all sorts of lengths, all sorts of diameters, but where do you think this would add value to the engineers on this webinar? Where should they maybe look first? And it's a good alternative to what they might be trying to do.
I would say primarily in busy urban areas with high ferrule densities. Because that's really where we sort of make savings if we install semi-structural linings, because we don't generally have to re-excavate the ferrules to remake the surface connections. So pipe diameter range, 3-inch up to 12-inch, I would say, as urban areas. You want quite large programs. You don't particularly want one-off odd lengths because you've got a reasonable amount of equipment to move around to get on site. So we kind of like reasonable scale projects rather than sort of odd 100-meter lengths here and there. But yeah, busy urban areas where you can't really dig, excavate, or you've got a lot of other utilities in the way as well.
Thanks, Chair. And then Steve, again, I appreciate with both of you, it's a big spectrum of things you can physically do with this technology. But again, what sort of project would be like you wouldn't hesitate, you haven't got to think very hard about it? Is there any particular atypical sort of things?
I mean, we don't anything where there's a too high a frequency of branches and connections. We can make branches and connections, but if there's a very high frequency, it's perhaps not suitable because you end up digging up every few meters. I think probably the two strongest targets for us are large diameter trunk mains, particularly in urban areas, and as sewer rising mains, as mentioned, and the sewer rising mains really of any size. We don't too small. It's not too small. We can do 100 millimetre, but to make it worth a while, we a good few 100 metres is probably what's needed.
Okay. We have a look on the chat. I'd encourage people if there's any other chat, and then we'll open it up with the mics. Somebody did raise a question about angles, what angles and bends. You did start mentioning what you could or couldn't do, but if I start with you, Jeff, on sort of angles, if you were drawing a spray lining head through, what are your sort of kind of flexibility or constraints around sort of bends and angles and so forth?
Generally, we're pretty content with sort of 22.5 degree bends. The diameter's important, really. The bigger the diameter, the easier it is to go around sort of sharper bends, really. But 22.5s, yes. 45s, well, would like a look at that, but could say yes. We generally like bends pretty much at the sort of start of a lining near one end, because if you pull through the bend, then you've got a nice easy pull of your sort of lining equipment down the straight, really. We wouldn't really want to sort of like have a bend immediately next to the lining rig, so the full lining is conducted, if you like, by pulling the umbilical hose around the bend, because that can introduce ringing into the lining. So we like the bends to be near the start of the lining, at the far end away from the lining rig, come round it relatively quickly, and then you've got a good straight easy pull.
Dave, yourself, I think you did mention, and it looks like with your pre-survey, you're kind of preempting what you may or may not be able to cope with. Is that a similar sort of degree of bend that you can look at?
Funnily enough, it's not very far away from what we can do. So yeah, 22.5. I don't really have an issue with it. But you'd need a large number of them going in opposite directions to make it, impassable. 45s can be got through, but that tends to be on land. I know, and this is always a surprising case study, that I was designing these around the world, so I've seen quite a few of them, these projects. There was one in Sydney where they went round a 45-degree bend with SDR11. I think it was 500 millimetre. So you wouldn't imagine that was possible, but it has been done. So with a 45, I wouldn't want to put a 45-degree bend in the middle of a kilometre-long pull. But if it was part of a short pull, we'd almost certainly be able to get around to it if we've done the correct surveying beforehand.
Okay. Good. All right. I'll go quiet for a sec and then just see, is there anybody else who wants to kind of put their hand up and or just put the mic on and ask some questions of these guys while you've got them here in front of you with all their expertise? Quite quiet. You must have convinced them, I think, with all the way you went through. I thought the presentations were great because you gave the history, you gave the background, you gave the what you can do in the kit. I got another couple of questions then to kind of close it off. We've done the sweet spot, we've done the angles. What about the kind of global experience? Because it feels like both of you, we're re-educating the UK market, is what it feels like from the way you guys have spoken, that these things have been well used, well trodden, but unfortunately that momentum was lost, and now we are in it re-educating mode, and obviously as a society we're keen to do that on your behalf with this technology. But where in the world are people using this stuff where they're like, wow, they must be thinking the UK's doing loads of this and we need to do some. Jeff, where are you finding you're getting a sort of a kind of a take up?
The Americas are good. Canada, South America, starting to pick up work in various countries around Europe. So sort of looking at the new EU drinking water directive as being the approval that's going to be required from 2027 onwards. But yeah, pretty much everywhere other than the UK, really, which bit of a shame.
It's slightly embarrassing exporting
Yeah.
a technology around the world, but we're struggling to use it because of some barriers that we've kind of put in the way. One thing that Jeff and me discussed for the audience is we know that the 3-hour rule as a reporting rule means that there's an incentive involved. With the amount of work that's about to take place across the UK market, one does wonder about two things. One is if you did a shorter lining length, would that overcome it? But you'd still have a least disruptive technology because the costs of reinstatement and everything else have gone up over the last 20 years. And could you comply with the 3-hour rule? The other challenge I would lay down to the industry as a society is how much is your incentive worth? It's a dramatic kind of thing to say, but we can say it as a society. If your incentive is giving you 10 million quid, but it's going to cost you an extra 40 million, has anybody run the numbers? So it's quite an interesting challenge to put forward because that is the biggest barrier to spray lining as we see it for Jeff or other spray lining systems. So it's not exclusive to what Jeff does, it's to any spray lining technology. So anything that could uncouple that would be good. Steve, global experience, kind of what?
Yeah,
Where's
I mean,
the
the
interest
Americas
at the
have
moment?
used it very extensively.
Sorry, Jeff. Sorry, what was that?
Sorry, I'm speaking. Can you hear me?
Yeah, sorry. Where did you say, Jeff? Steve, sorry, Steve.
So yeah, the Americas very extensively. South America, yes, but also Australia has been a particular area for this, and the Middle East as well. So, and by that I'm meaning both the dye technology and the roller reduction technologies, and but yeah, there is a big outfit. There is, well, there's three decent sized outfits in North America who use these techniques globally. But I think if I can just go back to the UK, I think what we're finding, I had 20 years out of the water industry and I came back to it. And what surprised me is, just as you say, half these technologies seem to have forgotten about. And they used to have a method selection methodology or a method selection chart in many of thof water companies that they no longer have, and they're just defaulting to, and off what have been part of the problem here, because Ofwat don't seem to understand the technologies that are available. So they're prescribing things without understanding what the alternatives are. And it's this, we're finding we're having to re-educate. I mean, we do a bit of work with the P100 Plus Association, and they said they'd been really surprised because they'd been going to engineers in the UK and found that they didn't understand the material and the basics of welding, and we seem to for some strange reason we seem to have gone backwards very much.
So, all right, well, it sounds like we just need to continue. That's our job, to educate and inform and provide people with these options and give them that understanding. Just to add to that before we close, we've certainly got more engagement from design engineers now, which is great. We've seen a change in the last 2 years where some of the large global design houses, kind of household names that you'd expect, are getting more interested in this stuff, which we'd really encourage, and for their active participation. And one or two of those are actually sort of tackling that issue of what guidance do we create as a design house, independent design house. And likewise, maybe to give you some idea, we were with a major water company on Monday, and they were talking about introducing or reintroducing a kind of picking list to give their teams at least the first look at what the options are. Now, what we're not saying, and we'll never say this technique is the technique, what we need to do is just make sure people are well informed. And then as they roll the detail of what they're doing, and like you guys have discussed where the sweet spot is, then you sort of hone in on maybe one or two techniques. But at the moment, it appears that that guy, almost like that feeder kind of guideline, isn't there. So we are encouraging people to look at both on rehab and new installation as well. Interesting, it's the same with the new installation. So thank you for that. One last call to anybody on the call who wants to throw a question in. Otherwise, I will just do a final share of the screen, if I may. Just bear with me. Let's have a look and go back to the slide here, which was Jeff's last one. And let me just move that forward. So we've given that talk, we've done the panel, and can you see that okay, guys? So it was just to close. Thank you all for being on the call. These are some other, if you look at the top left, you can see the new 2 meetings around site investigation and condition. That links clearly to what the guys have talked about. We'll be having a session on that in May. Infiltration as a topic in its own right. How do you stop that? That's on the wastewater networks, and then cured in place rehabilitation, and that will cover pressure and gravity in November. Those involved with capital schemes, the masterclass at the end of April, we are going to look at some of this technology we've discussed today, but we're also going to look at things like microtunneling, directional drilling, online replacement, and various other technologies. So for those of you involved in that masterclass is a more of a workshop environment in one-to-one in a hotel room where we've got some experts matched and mixed in, and you'll be most welcome to sign up for that and bring any projects along which we can discuss. And then the last bit there, you can see the road shows. London, for those who are based in London, Thames Water are putting on a really good event for us. 5 different technical presentations led by their project managers and by their partner contractors, talking about 5 different types of no-dig technologies. Really, really great. And the big event